So the recording for Tuesday, when I ended the class, it gave me a message I've never seen before, but basically said something happened and it lost the recording. It didn't say I did anything wrong. So there's no recording of our actual class Tuesday. I figured I must have said something that wasn't allowed to be recorded, and Zoom decided to. But last year I did record, and those this whole week is there. And so it's actually just me in the classroom. You can pretend like you're in the classroom with me. And so I apologize for that. The notes are similar enough. And so there's 4 videos, and it says what the topic is for this week. So the first one's on electronegativity. The second one we're actually going to do tonight, or I'll just have you watch the video. And then the third one was all the Lewis structures. So it's actually shorter than when I did it on Tuesday. It's condensed into an hour instead of 2 hours. So you only have to watch an hour. All right, let's go ahead and go through the study sets. Hopefully you guys uploaded your study set. You remember how to do that. Worksheet was pretty gentle, the first worksheet. The first few, because they're diagrams, most students tend to do really well. It could also be that this is my specialty, is molecules. So, all right, which ones can go more than 4? This is more than 4 valence pairs. So this is pairs, so over 8. And it is any of them that are after aluminum. So once we get into the third row, the d orbitals, the reason when I said why is they expand into the d orbitals. And we actually talk about this next week quite a bit. So they expand into the 3D. So that would be selenium, phosphorus, and chlorine can all go past that. A quick comment about boron. Boron actually goes to less. The 3 that I circled go to more. And boron actually ends up less than the octet. All right, and then number 2, we are going to draw Lewis structures. So count your electrons, which is 20. So again, a reminder, sulfur, the A group numbers are easier, but has 6 valence and then 2 fluorines, so it's going to have 20. The center is almost always the first element, single line. And again, your lab for this week, which is due by Sunday, this is what it is. And I will have, I can stay after today if people, it's, this extremely beautiful weather. We're all from Oregon, and we know, enjoy it while we've got it. And so I bet it's great that it's the first week and there's not a lot to. Give your octet to the outside and then put the extra on the center, and we're done. We're good. That's all there is to it. This one, SB, is antimony, so that one has 5 valence plus 21, so 26. Make sure you do it, for those of you who like to work only with pens, who don't like pencils, make sure you can erase, because when we have to go, or make a sketch and then transfer it, extras go on the center. So no double bonds, back to the question that happened. And then for this one, there's going to be 16. When you do it, you're going to run out. So you do your octet to the outside, you count, and then you put dots on the inside, but we've already used all 16. So this is when you've run out and your center doesn't have an octet, that you erase and go backwards. And then back to the comment about the video. I think last year when I made the video, I was much more professional than I am now. I'm done with this teaching method. I will have an answer for you guys hopefully next week how summer's going to run, because we're meeting next week. I don't know if they'll give us, yes, you definitely can be on campus, but they might at least say it's a possibility. So I'm hopeful. I'm ready to be back on campus. All right, so the Vesper, you can circle your clouds if you want. I'm going to do it for this teaching, that the first 2 both have 4 clouds. And in all honesty, since we're in this environment, the lab, the handout we did the other day walks you through each of the possibilities. So like the first one comes out, the tetrahedral bent like water, or your lab has a chart condensed down. And once you get through the lab, you're going to actually know them. We work with this week and all of next week. And so it's just a lot of drawing and stuff. Last year, we were actually like going, oh, we're fine to be online for the first few weeks because the labs are paper labs anyway. I had no idea it would keep going on and on. So this is a tetrahedral or a tetrabent. The tetrahedral is the Vesper geometry. The bent is the molecular geometry. I didn't ask for the molecular geometry, but I am going to at some point. If it's a tetrahedral, you can just say 109. Again, it's technically like closer to 104, 105, but I'm good with 109. All right, this one is a tetrahedral pyramid. So it has 4 clouds and 3 bonds and 1 lone pair. We should say a triangle-based pyramid, and tetrahedrals are always around 109. And then this one has, they're just 2. This one's linear, 180. So questions with that. The key is drawing the Lewis structures. You got to get the Lewis structures right, and then the rest of it just falls in place. All right, question number 2 ends up being the one that a lot of people ask about because polarity, you're looking for if it's symmetrical or not. And so our last one here is nonpolar because it's the same the whole way around. Sorry. These other 2 are polar. Bents are pretty much going to be polar, and pyramids are going to be polar. The only way they would not be is if there's no pulling happening from the center, if like they all are the same. We saw that with the ozone. All right, and then question number 3, I didn't actually specifically talk about. I kind of mentioned, and you can gather or Google hydrophobia. Phobia is fear, and hydro is water. So this is beyond human fear. Human fear is an emotion, it's an illusion. So when we say we're afraid of heights and stuff, these guys don't mix with water. So they do not mix with water. So they do not mix with water. And that would be something that's nonpolar. And so I did mention that, I just didn't use the word hydrophobic. And so I apologize. So does anybody know what the word is if something loves water? So like our first 2 love water, they would definitely mix with water. It is in the notes for tonight.
Hydrophilic?
It is, it's hydrophilic. So Philadelphia, phil means love. And so Philadelphia is the city of brotherly love. All right. They have that big love statue you can go see. All right, so more of these. This one, count our electrons. I'm counting 28 plus 6. This is going to have 34. Don't assume it's tetrahedral. So your celebrations, everything's going to be show your work. So you're going to have to be drawing Lewis structures. And when you do your dots, so there is a question that often comes up, and it might show up in the notes tonight. There's only so many possibilities, and so like whenever you get certain numbers, you always end up with certain shapes. So this one has this lone pair, those extra ones go on the center. All right, PF5 is going to be 40. So this one works out. This is just going to be the P with the 5 fluorines. And, oh, I know who's missing. So there's no lone pairs on the center. So just count by 8. So 8 times 5 is our 40. This one is going to be 36. So a quick comment. I don't think I said this the other day. So noble gases do not make compounds in nature. However, helium and neon have never been made into a compound, as far as I know. I don't think argon has either, but krypton and xenon and radon, they have been able to force them into compounds with something that's extremely reactive, like fluorine. And so this is a man-made compound. I mention that because I've had students in the past who leave the answer blank and just write, can't happen, it's a noble gas. If I'm giving it to you, it's saying, yeah, somebody's made this. There's a question that shows up on one of the worksheets next week that's even more bizarre, that they've actually forced an iodine. They took an iodine and they were able to put 7 fluorines on it. So it ends up going to 7 orbitals. They've actually gotten to 8 orbitals now, and they come out really crazy looking. But yeah, in this wonderful online environment, you can Google some interesting. I don't know what the use would be. And again, those of you who are going towards medical fields, really, you're not going to go past the tetrahedral, unless somehow you end up teaching a general chemistry class. All right, so the extras, we get to 32, and then the extras will be there on the xenon. Question that Omar had asked, you can show them like I have them, you can show them here and here, but you do want to show the lone pairs as pairs, because electrons do always pair up. And then I think we're going to describe them. So 5 orbitals. So if you have 5, this is a trigonal bipyramid. And then a seesaw, because of that one lone pair. And describing, you're going to have columns, nice boxes to fill in like on the lab. It makes it really easy for me to grade also. So this ends up with 180, 90 degrees, and 120. It has 3 bond angles, and it is polar. Seesaws are polar. These are really bizarre, but they happen. And one of the things you're going to notice with a lot of these that do the expanded octet, you're going to see fluorine or chlorine. You're going to pretty much see the halogens showing up. And so they're man-made compounds where they were able to force them to go to an expanded octet, because why not? All right, trigonal bipyramid. This is, again, if you have the same answer for if there's no lone pairs, this is our little chart. The Vesper geometry is your total number of clouds. So the total number of clouds here is your Vesper. Yeah, electron pair. And then the split of the different types of clouds, that's going to give you your molecular geometry. So the Vesper, if there's no lone pairs, the Vesper and the molecular geometry are the same thing. So you can just answer it one time, or you can answer it twice. But this one, right, the angles are there. And I will have to tell you this, back when you didn't get the chart on your exams and stuff, people did really good with this. Because there's really only that many. It's good for your brain a little bit. All right, this has 6, so 6 is an octahedral. And again, an octahedral is a square and then something above and something below is what it looks like. And it then comes out as square planar. So the lone pairs are above and below that plane. So everything's in the same plane. Very different from a tetrahedral. Since it's a square, it is 90 degrees. Now, something I didn't mention, and we were all tired, it was the first day. I've had some students say, well, isn't it 90 degrees and 180? I don't care. That's my answer. So if you are somebody who says it's 90 and 180, great. I really don't care. You have to have the 90 there. The seesaw has that 180. It's like a whole other piece of thing. All right, when I do ask you to describe, there will always be that column that says polar, non-polar. Please notice on my chart, you cannot make a generalization and say linear is always non-polar. You really have to look at the situation. And we'll see some of those examples on the back. So the middle one is nonpolar because everything's the same the whole way around. And by the way, the triangle bipyramid is a triangle in the middle and something above and below. The seesaw is polar. And the last one is actually, in this case, nonpolar. So after we go through the study set, we'll look at isomers and we'll see other possibilities here. I'll keep going. There's no questions. All right. So acetylacetone. This is like a really fun word to say, tautomeric. Those of you who are going to be in organic chemistry, you'll run into that word. So tautomers are these guys that, if you look, they have the exact same. Oh no, that's somebody different. There's different. This one's showing the same. So we're going to see this on the next study sets and worksheets that you're going to start seeing pictures like this. I don't know that we did many of these. I don't remember doing any of these on class on Tuesday, but you do want to look at the lone pairs. So on this picture, I was really nice to you. You can see the lone pairs on the oxygen. Organic chemists don't show those lone pairs. You just have to know they're there. But our bond angle here, we're just doing angles. This would be 109. Again, if you say 104.5, that's fine. I don't care. Number 2 is going to be 120 because the carbon. So if you look, the oxygen has a bond on each side and 2 lone pairs. For the carbon, you have 1, 2, 3 things around it. So you kind of have to, you learn how to look at just that one piece. If you have to, you can always cover up around it and say, okay, I have a double bond on this side, a single and a single. So there's 3 things. It's a triangle planar. It just takes practice. And this one also, it's saying this bond angle, so this would be 120. This picture here is really nice. This would be if we were in lab where they actually show the bond angles. So you can see better that number 3 is 120 and that number 2 is 120. All right, and then these were the same picture. So 1, 2, and 3 are the same thing. I apparently didn't print in color, so you can't see the nice colors. Over here, number 1 is 120, 120, and 109. So quick comment, if you're seeing carbons, oxygens, hydrogens, organic molecules are carbon-based, you are not going to be doing any of this stuff with the octahedrals. So carbon compounds are not going to break the octet rule. So you're going to be restricted to tetrahedrals, planar triangles, and linear. All right, number 7 is talking about NO and NO2. So this happens all the time, especially in Philadelphia. So I'm from New Jersey. Not here as much, but whenever there's lightning storms, so the lightning is enough energy. So nitrogen, take a step back. N2, the atmosphere, right, is over 70% nitrogen and 20-some% oxygen. Nitrogen is actually triple bonded. And because it has a triple bond, it's not reactive as N2. You need a massive amount of energy to break that triple bond or a really good enzyme. So that's the whole thing with putting certain plants in your garden. If you have a garden, so peas, legumes tend to break the nitrogen down and provide nitrogen for all the other plants and stuff. But anyway, when lightning happens, it can break the triple bond, and then the nitrogen and oxygen react, and you get a whole bunch of compounds. If you add up your 6 plus 5 is 11 electrons, and this would be what, 12 plus 5, 17 electrons. These are going to give you an odd number. And so the dilemma becomes when you try to bond the nitrogen and oxygen, you're going to end up with a double bond. You give the oxygen, it's got 2, 4, 6, 8, 10, 11. You end up with a free radical. There's no way you can balance it out. And so that's all I was asking on that one. I don't know if even asked you to draw them out. I talk about free radicals more, I think, next week, but free radicals, they're gonna search for that other electron it's missing. And so these are not good to be around. Ozone is really good at creating free radicals also. And that's why a lot of people actually treat, there's a thing where you treat water with ozone. And that's because it kills the bacteria because of its ability to create free radicals. Was there any questions on that first page? Go ahead, Major.
On the very first one, could you explain why it's you have like more than 4 valence electron pairs?
If you're, the ones are going to be, if they're beyond aluminum, after aluminum, we don't, when we draw the orbitals, we don't show the d electrons, but the d orbitals are available. So this is the 3 Ps, right? So if you're at chlorine, the 3 Ds we're taught are down here, but if you're in the third shell has S's, P's, and D's. So we don't show the electrons in the D's, but they're there. Does that help a little bit? Yeah. We work with it more next week. So I have it as a question on the study set, just so you're aware of it, and then we work with it more next week. And so you're not the only one. That question's asked every year. Anybody else have a question from the first page? All right. So this page works a lot with polarity. So the more electronegative, oh, that's the chart I can't find, is fluorine is the most. So you can show it as a negative and a positive, or you can show it as an arrow. And so that's what I mean when I say indicate the polarity. Either way is fine. It's really up to you. And then circle the more polar. The further apart they are, the more polar they are. So carbon oxygen is going to be more polar because carbon to oxygen is 2 spaces apart. Carbon to nitrogen is just 1. All right, boron, oxygen. Oxygen's always going to be pooling, except if it's with fluorine. And then, sorry, I have to find if I have a chart. Go, maybe. So I have to look at the chart for some of them. Boron and sulfur are far enough apart. And the general rule is as you're moving towards fluorine's corner, sulfur is much closer to being over there, that it's going to be the one that's pulling. I personally prefer arrows, and the oxygen one, if you see something with oxygen, unless there's fluorine, like this one, the fluorine is definitely going to be the more electronegative. And then the boron iodine, I would actually have to look at them. Yeah, apparently it still pulls. All right. So you guys have a bunch of charts. You're going to want to make sure that those charts are in a nice place for you to look at to compare them. All right. The phosphorus bromine. Again, it's a big enough difference. More than 0.4 is what we're looking for. So greater the electronegativity, the difference in electronegativity is greater than 0.4. So bromine is going to be pooling. So the higher one is the one that's pooling, the one that's closer to fluorine. And the chlorine one's going to pool even more. So again, as you're moving towards fluorine, you're going to be pooling more. So the one with chlorine is definitely going to be a bigger pool than to bromine. So it's this corner up here, the nitrogen, oxygen, fluorine, that really pulls. Something I didn't point out, these are all little nuances, but again, nitrogen, oxygen, fluorine, that corner, we keep coming back to that NOF. N, O, and F, they're going to be very special. People keep changing the rules, and I don't know why they have to do that. But chlorine, it comes out almost the exact same number as nitrogen. And so Linus Pauling was happy with 2 digits, And so the newer charts go more and more digits, but that's kind of a weird nuance that nitrogen and chlorine don't pull on each other. All right, so questions 8 and 9 are kind of these hypothetical questions. So if something is linear, this is our center, the A. If it has, so this one's linear and this one's linear, if it's the same on both sides, right? The A's are going to be pulling against the Y, but they're going to pull equal but opposite. That's going to be non-polar. But this one is going to be polar. Even though we don't know what X and Y are, one of them is going to pull more. So if we think like the X is pulling more than the Y, it's a whole thing with vectors that the one's going to definitely be pulling. It's not equal. All right, angular means bent. And you can make a quick sketch. It doesn't really matter what kind of bend, but we have a bend. It's going to be lopsided. There's going to be a pull, so this is polar. And then this one, it's again a bent. If you want, you can show your dots. Doesn't matter how many dots. It's the idea that you have a bend. It's going to be non-polar because they're all the same. So none of them can pull on each other. So even without drawing, it doesn't matter what the shape of this molecule is. No matter how you would draw it, it would come out non-polar because nothing can pull because the center is the same. All right, on number 9, planar triangle. So you would have your center, and it's saying our center is X, and it has 3 Y's around it. And so if it's planar triangle, there's no lone pairs, so it would be non-polar. If it was a pyramid, it's saying there's a lone pair, and so it's not equal. So that choice would be C. So B and C are true. They're the ones that are possible. All right. On this number 9, so Araceli, you'd asked me a question earlier, and I'm noticing my numbering is really funky on this. You would want to draw your pictures, and you're going to end up with your dots on the center. So if you draw it like this, and I want you to indicate polarity, you're going to have to redraw it because it's not going to be easy. This is bent. So if I want you to show the polarity and it is polar, you're going to have to redraw it where you can see the bend. And that's probably going to happen like one time, like it only happened once on the study set. And so the outside ones are almost always what is pulling. So the pull is going to be towards in between the chlorine. So there's a pull that way. And that's how you can indicate it. On this, we have a carbon, hydrogen, 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 and chlorine. So each hydrogen is 1 electron, 4 for the carbon, that's 7. So we have 14 total. Carbon loves to be a tetrahedral. This has a pull. Chlorine is going to pull. So you can do it with the arrow, pulling to the chlorine, or you can show that this is our negative area and this is our positive area. Again, either way is fine. Pick the way you like and just go with it. All right, SO3. Count your electrons. There are 24. So always do your Lewis structure. You draw your oxygens. You give your octet to your oxygens. And we have a problem. 888 is 24. So if you read my story, you don't have to read the story, but if you do, this is the punchline of the story. This is not the correct answer. What's wrong with my picture?
The sulfur is missing.
Yeah, the sulfur. The sulfur doesn't have its octet. So always take care of the outside, and before you start doing anything, you have to look at the center. We've run out of electrons. This is when you make a double bond. And again, this is why when you get through your lab, you'll have this down. And it doesn't matter where you put the double bond. Wherever you erase the 2 electrons, that's where you'll show the double bond, but this is a resonance. And so bonds do not pull, atoms pull. So it's not that you say, well, this is polar because it's asymmetrical. The bond doesn't pull, it's the oxygens. All of these oxygens have 8 electrons. It's just distributed in different ways. So all the oxygens are pooling, but they're all pooling equally. So this is nonpolar or hydrophobic. It will not mix with water. So the other 2 are hydrophilic. They're gonna love water. All right, nitrous oxide, we did this one the other day. This is nitrous oxide that dentists use. So any of you pre-dental, you can do your compound on nitrous oxide. There's so many possibilities. Pick something that you want to learn more about, or that you think you can do. There's like a billion trillion compounds out there. So pick something that you think you can do something really fun with. All right. This is the one, so we're going to have 16 electrons. And this is the one I did the other day. Nitrogen goes in the center. Why do I put the nitrogen in the center and not the oxygen?
It always wants to pull.
The oxygen wants to pull, right? The nitrogen's the least electronegative. So the least greedy goes in the center. And so there's no rule to make it nice and balanced. The other thing that's interesting is when we put our dots, we've run out and we have to start bonding with the center. So we're going to need 2 more bonds. And this is where it does not equal out. Because again, the oxygen's so greedy that you do end up with a triple bond. We're going to go through one like this tonight. Hopefully not this one, but we'll see. Because there's a thing called formal charges that I have to teach tonight. Not looking forward to it, but I had a good day. So there we go. This is going to be linear. And it is definitely polar. The oxygen is pooling. So it is lopsided. It's probably partially why it works so well. Right, and you should floss. Flossing is really important. All right. So now number 11. CH4. Carbons make 4 bonds. The lab next week is organic chemistry. And so it's a video you get to watch of me. It's actually 2 videos because I was learning how to make videos. So it's about an hour and a half, the 2 videos, and it's 8 pages. And you just follow along the video, the notes. We usually would do it all together, but last year I was in the habit of making videos the first 2 weeks. And so you'll get to watch that. It does require us to have Tuesday's lab because several of the pages, and then there's 2 pages that are post-lab, and those are the 2 pages you'll submit. And I'll talk about that next Tuesday. Some of the information that we will cover next Tuesday, you will need to do that lab. All right. This one's an interesting one. So we have 21 plus 3, so 24. You give your octet to the fluorines. And this is actually important. This is nice. That one had 24. This one has 24. We don't make a double bond on this one. So there's going to be little pieces of information I add today. Halogens don't double bond. Why?
Is it because they're so greedy?
They're halogens, right? It's like they're halogens with more. They have 7 electrons. To go from 7 to 8, that's 1 bond. So these guys are going to make single bonds, and that's it. Oxygen needs 2 electrons to become an octet. So oxygen is going to make either 2 singles or it can make a double. Sometimes it breaks the rules, but We are not fluorine. I'm sorry, boron is the one that it's less than the octet. It was in the very first question that boron is less than the octet. So that's all that happens on this one. All right, NH2Cl, we have 714 electrons. So this is telling you the nitrogens. We're gonna go have more than one center tonight. I'll show you what to do. It shows up on the lab. I tell you, there's one page where you have multiple centers. So you have 8, 10, 12, and then the extras go on hydrogen. And so these are Lewis structures. And our last one is 16 again. So carbon, we're going to end up with double bonds. We did this one already. All right. So bond polarities. Let's see, bond angles and bond polarities. So the last one, this is 180 because it's linear. And it is non-polar, but that's not what I asked. The bond polarity, it is pulling. The sulfurs are pulling, but they're going to be pulling equal but opposite. On this one, this is non-polar. So that's kind of a trick question. You have to have a chart. So I put it in the homework. Nitrogen and chlorine have the exact same electronegativity. So they don't pull on each other. It's like people who love trick questions. That's like the ultimate. So this part of it doesn't pull, but there are hydrogens on the nitrogen. So sorry, I should have said this part is nonpolar. So the nitrogen, I didn't draw this very well, but the nitrogen, the pulling is like, the nitrogen is pulling on the hydrogens. So the pull is towards the nitrogen. So there is this polar part, but the nitrogen, sorry, the nitrogen to chlorine is nonpolar. That's how I should have said it. The molecule itself will be polar. It will like water because of the NH. The bond angle is around the nitrogen, and there is that lone pair, and so this is going to be the 109. This is a triangle pyramid. At BF3, 120 degrees, and the fluorines are pooling. You can actually show it in the bond, but it comes out overall nonpolar because they pool equal but opposite. Carbon hydrogens, no pooling. Nonpolar bonds. Neither pools. The difference is not big enough between carbon and hydrogen for there to be a pool. So that was the same with the nitrogen and chlorine. There's no pool, but there is a pool between the nitrogen and hydrogen. All right, and then I guess I have some questions. Which compounds have polar bonds, but no overall polarity? The last one, the CS2 and the BF3. So those guys each have pooling happening, but nothing else. Which one is going to have the most polar bond? Fluorine. See fluorine? You're going to pick BF3, so B. And the hydrogens are always going to be the positive. They're going to be positive. That's why we show hydrogen over on the positive side of the periodic table. All right, so questions on this page. All right, I'm going to stop that recording.